Okay, so we will be looking at week 6 topics today. In week 6, is my screen visible?
Yes, ma'am.
Okay, good. In week 6, we will be seeing mainly matrix algebra, which is something which you all of you must be knowing these things like basic addition, multiplication, right? And then row and column space of matrix products, finding inverse powers and determinants. You might think that all these are like, what is new about this? I know everything, right? How many of you feel like that? All the topics look very familiar, right? How many of you feel like that? No one feels it that way.
Yes, ma'am. Yes, ma'am.
Yes, right? Like these are
Yes.
like very well known topics. What's so new about it? Okay, let's see what you are able to learn newly from this week. Okay. Okay, so addition is something which you know usually. Like matrix addition is nothing new. Like if you have two matrices, you know how to add. But when you look the matrix as representation of the transformation. Now, what is the sum of two transformations? So let's say you have two transformations T1 and T2. Okay. So now what is T1 plus T2? It is another linear transformation defined in this following way. Now, what is the matrix representation of this sum of these two transformations? Okay, that is nothing but sum of the matrix representation of T1 and T2, the usual matrix addition. Okay, so M of T1 plus T2, the matrix representation of this new operator T1 plus T2 is nothing but M of T1 plus M of T2. Okay, this is something very straightforward. You can see it very easily, right? So like addition is very natural, right? You are doing the coordinate wise addition. But multiplication, matrix multiplication, how many of you think the way it is defined, it is really strange, right? How do you do, for example, some very simple matrix multiplication? 2 minus 1 1 0, and then you have 1 3 5 and 4. Okay, how do you do the matrix multiplication? You take the first row, multiply it with the first column, right? So what you get, 2 times of 1 minus 1 times of 5 plus minus 1 times of 5, which is minus 5, and then first row with second column, right? So 6 minus 4, and then second row times of first column 1, and then 0, and then you have 3, and then 0, right? How many of you have thought that why matrix multiplication is so different? How can matrix multiplication be like defined in this way? Who thought about this way of multiplication? How many of you have thought about this? Right? Multiplication is not at all something very naturally you can see. Why first row with first column, second column? Something very different, right? How many of you have thought about it? Yeah, right? Okay, let's see whether we get an intuition through linear transformations, right? Okay, so just like we saw that sum of two matrices represents the linear transform sum of the linear transformation, similarly product of two matrices also represents the composition of the respective linear transformations. So first, what is composition of linear transformation? So if you have two transformations, let's say T1 and T2, provided that here you see that this domain should match with this codomain if you want to define T1 composition T2, because can you tell what is the size of the matrix for T1? Yeah, what is the size of the matrix for T1?
M into N.
N cross M.
M cross N,
Cross
right?
N. Yes.
And for T2?
N cross K.
Yes. Okay, and we know that for multiplication, matrix multiplication to be defined, we want these two numbers to be same, right? So if we want to multiply this matrix together with this matrix, then only when these two are same, then we can multiply. right? This is the condition for matrix multiplication. But from where do this condition come? From the transformation property. See, when usually composition is defined, so T1 composition T2 is defined only when this domain is matching with the codomain of T2, right? Only then we can have T1 composition T2 defined, right? Because what is the domain of T1 composition T2? T1 composition T2, what is the domain? The domain is this, right? The domain of T2. This is the domain. And what is the codomain? So here it first goes through Fn, and Fn is common for both, and from Fn it moves on to Fm, right? So you see that we start with an m by n matrix and n by k matrix, and the product, you know what is the resulting product, size of the product? If you multiply two matrices of size m by n and n by k, what is the resulting size of the matrix?
M into K.
Yes. And you see that that is the order of T1 composition T2, right? Here K and here M, right? So this is the first relation you can see between composition and the matrix multiplication, the order. Okay, this is first observation. And next thing, in general, how do you represent matrices with transformation? Okay, so suppose you are having some transformation, right? So you are having some transformation from Fn to Fm. How do you find the matrix representation? Let's say with respect to canonical basis itself. With respect to canonical basis itself. How do you do the matrix representation? You find what is T1 is the first column, T2 is the second column, and TEN is the nth column. Right? So this is the usual way of finding the matrix representation. Now, in place of T, we are having T1 composition T2. Right? So in place of T, we are having T1 composition T2. So the process is going to be exactly the same, right? So that is what is going to happen to represent T1 composition T2. So first what we have to do, we know what is M of T1, what is M of T2. Now we want to find what is M of T1 composition T2. Remember, for T1 composition T2, what should be the columns? The column should be T1 of T2 of E1, T1 of T2 of E2, and up to T1 of T2 of En, right? This is how we have to represent, right? So hold on here, what's the domain of T1 composition T2? K. So it should be up to K. This is how we have to write the matrix representation of T1 composition T2, right? So now what is T1 of T2 of E1? What is the first column? Okay, so first column, you see that T2 of E1 is there inside the bracket. Now what is T2 of E1? This is T2 of E1, right? This one. So here we are writing T2 of E1. Now T1 of E1 is, this is the matrix representation of T1, and this is your vector here. So how do you obtain this? You simply multiply M of T1 with this vector and you get this, right? So how do we get this? So you see that, so this is B11 times, what is this? B11 times, what is this?
Row
First,
of MT1, first row.
first row or column? First column of A, right? Let's call this A, for example, E for just easier convention. Okay, first
Yes,
column of
first
A, right?
column.
Yeah, same way you can see that this is nth column of A, right? So you see that T1, T2 of E1 is simply a linear combination of the columns of A. Similarly, T1 of T2 of any EI is going to be a linear combination of the columns of A. So what are the columns of M of T1 composition T2? Is that clear for everyone? Yes. So now each of this column, so each of this column is of this form, right? So T1 of T2 of EI is of this form. Is that clear for everyone? Yeah, so far? All right. Okay.
Yes.
So now you see that M of T1 of T1 composition T2 is nothing but, so this is the first column. This is the first column. And if you put EK, then you get the kth column, right? So you see that this is the general ith column. Okay. Now, how is the usual matrix multiplication done? Do you see that they are same? So if this is a matrix, this is another matrix, A11 B1 plus A12 B1 B21 and so on. So this is how the matrix multiplication we are doing. Do you see it is in alignment with the matrix representation of T1 composition T2? Now do you
Yes.
have some feeling of how this matrix multiplication concept came? Yes?
Yes, ma'am. Yes, ma'am.
Good. Okay. So here what is that we have understood? So the matrix multiplication, okay, matrix multiplication here, you see M of T1 into M of T2 is the representation of the linear transformation T1 composition T2. Okay, so here M of T1 composition T2 is same as M of T1 into M of T2. All right. Okay. Just a quick example. How many of you can quickly tell the answer for this? First of all, what is the size of the first matrix? Let's call this A and the other one as B. What is the size of A and what is the size of B?
Four
Having
into
1
one.
cross 4,
And
B
one
having
into one.
4,
That is
1 into 4 and this is
4 into 1.
4 into 1.
4 into 1.
So the resulting matrix should be of the size 1 cross 1,
1.
right? So what's the
Yes.
answer? Is it correct? Yeah?
Yes, ma'am.
Okay. So similarly now what should be the first, what is the order of A and what is the order of B? A is of order 4 cross 1
Cross
and B is of
1.
order 1 cross 4. So
1
here
cross
the
4.
resulting matrix should have size
4 cross 4.
4 cross 4, right? So here you see that you have first row, first column, first row, second column, right? And then here you have 2 4 2 4 1 2 1 2, then 0 0 0 0. Is that correct? Yeah. All right. Okay. So what is one important property about composition of transformations? So composition, so just like matrix multiplication, the order in which you are going to multiply. So suppose let us say you are going to do matrix multiplication for three matrices A into B into C. Does it matter whether you do A into B first or B into C first? Does it matter? No, right? Same way, the composition also, it does not matter in which order you are going to do. So that is, composition is associative. Okay. So either you can do first T1 composition T2 or T2 composition T3 and then do T1. So this is not going to affect the transformation. So transformation composition is associative. So you don't need any brackets when you are using composition for more than two operators. Okay, but is matrix multiplication commutative? Are they commutative? They are not commutative, right? They are not commutative. This is something very important. I guess in 2 by 2 case I have already given some examples, right? So if you can verify some very simple examples, maybe this one, here you have this one, this matrix itself. Okay, so this is A into B. Let's say this is A, this is B. Can you quickly compute and tell me what is B into A, everyone? Calculate B into A and tell me the answer. Yeah, it's just 2 cross 2
Yes,
matrix.
ma'am. Yes, ma'am. 3 minus 1, 11 minus 5.
3 minus 1, 11 minus 5.
Yes.
Okay, so 2 plus 3, no. What should be the entry here?
5 minus 1, 14 minus 5.
5.
Ma'am, I I have written wrong.
Okay, okay. Minus 1 is fine. And then here 14
Minus 5.
and minus 5. Yes. Okay. And it's very clear that AB is not equal to BE. Right? Okay. So matrix multiplication is not commutative. Okay. Commutative means AB not equal to BA. Commutative means what? Switching positions. AB is not equal to BA. Okay. Fine. So there is something which we have to understand in terms of rows and columns of the matrix product. We have to observe something first of all. Okay, so what is that we are going to observe? So this is the usual multiplication done. Okay, so let me take maybe 3 cross 3 matrix, then it's more clear. Okay, so A11, A12, A13, A21, A22, A23, A31, A32, A33. Then B11, B12, B13, B21, B22, B23, B31, B32, B33. Right? Okay. Now we will do the matrix multiplication. So you know that it is A11, B11 plus A12, B21 plus A13, B31. Okay, so this is the first entry. What's the second entry? A11, B12 plus A12, B22 plus A11, B, sorry, A13, B31 or B32. This is the second entry. And the third entry, it will be nice if you can, if I can write next, but anyway. So this is my, let's call this C. So C11, this is C12 and C13 I am writing here. C13. What is my C13? Can you tell? A11,
B13, A12, B23 plus A13, B33.
okay. So what do you observe here? So similarly, we have to write the remaining entries. Just let me explain with the first row first of all. Okay. What is that we first of all observe here? Okay. So let's see. here you have, what is the first row of B here? B11, B12, B13. So we are having A11 times of B11, B12, B13, right? Plus A12 times of, what is that we are having next? We are having B21, the second row, B21, B22, B23, and then A13 times of B31, and here B32 and B33. So this is the first row of C. This is the first row of E, second row of B, third row of B. So you are having three vectors and you are having a linear combination. So what is the observation here? Any row of the matrix multiplication AB, so you are having, this is your A, this is your A, this is your B, right? The product AB, the rows of AB are linear combination of the rows of B. Do you understand? Is that clear from this? Yes? Okay. So if not, please ask me again. So the thing you need to observe is that every row of the product AB, right, is a linear combination of the rows of the second matrix. Is that clear for everyone?
Ma'am. Yes, ma'am.
Good. In that case, what is that we see? Rows of AB are linear combination of rows of B. So this means what? The row space of AB, okay, the row space of AB is contained in the row space of B. So you take any row of AB, it is a linear combination of row of B. So the row space of AB is subset of row space of B, right? What is the row space of AB, by the way? So this is nothing but span of rows of AB, and this is nothing but span of rows of B, right? So here you see that you take any row of AB, then it is a linear combination of the rows of B. So row space of AB is a subset of row space of B. So if the spaces are subsets, then the dimension should be less than or equal to. So dimension of row space of AB is less than or equal to dimension of row space of B. And what is the dimension of row space of AB? It is rank of AB. Similarly, what is dimension of row space of B? It is the rank of B. So rank of AB is less than or equal to the rank of B. So how rank of AB is less than or equal to rank of B? Is that clear for everyone? Yes or no? Yes, no? Any comments? Let me know your comments and then I will continue. So, is it clear or not? Okay,
Yes,
the
ma'am.
others?
Clear.
Good. Okay, fine. So, there is another thing we can observe. What is the other thing we can observe? So, this is the first row we saw, right? Similarly,
It's
similarly,
not equals to A.
sorry, what? Someone was saying something.
Ma'am,
Rank of
um,
AB is not less than rank of A. Why is it not?
It's, yes, rank of AB is less than or equal to rank of A. Oh, sorry. Here
ma'am,
I
Okay.
rank of, okay, see, I move to the next slide. Rank of AB is less than or equal to rank of B. This is the first thing we have seen. Next we are going to see that this is also true, okay, but we are going to have a different argument for this, not the same argument but a different proof we are going to see. Okay, so the same matrix multiplication is what we are going to see. Okay, so
ma'am.
yes.
It is applicable only for square matrix, or it is
This is applicable for
different
any matrix.
A and B if they are both are
Different also it
under different.
applies.
Okay, ma'am.
Okay, fine. And then here, in fact, you see that the matrices taken here, they are not square matrices, right? So here m cross n and here n cross k. So just for understanding purpose, I have taken this, but you can take something different also. Okay. So here, for example, here if we are doing the similar thing, so here since you asked, maybe I can take something like 2 cross 3 matrix. So 2 rows with 3 columns. So A11, A12, A13, A21, A22, A23, and then here B11, B12, B21, B22, B2, B31, B32. Okay. Now what is this multiplication? So you see that the first column is A11, B11 plus A12, B21 plus A13, B31. Right? And what is the second entry of the first column? So A21, B11 plus A22, B21 plus A23, B31. Right? Similarly, here you will have A11, B12 plus A12, B22 plus A13, B32, and A21, B12 plus A22, B22 plus A23, B32. Okay, here what is that we observe? So here B11 times of the first column A11, A21 plus B21 times of A12, A22 plus B31 times of A13, A23. So you notice that this is your first, so let's call this C. This is your first column of C, right? And this is a linear combination of columns of which matrix? Columns of which matrix? A or B?
A. A.
A, right? So this is the first column of A1, first column of A. So second column of A and third column of A. So the columns of C are the linear combination of the columns of A. Okay. So you have to remember that for the product, the rows you have to compare with the row space of the second matrix, but for the column space you have to compare with the column space of the first matrix, because that is how the linear combination happens. Okay, so what is that we observe? Column space of AB is a linear combination of the columns of A. So column space of AB is a subspace of column space of A, and hence their dimension is less than or equal to the dimension of column space of A. And then what is the dimension of column space of AB again? Rank of AB. And what is the dimension of column space of A? The rank of A. So we got rank of AB less than or equal to rank of A. So an important observation here, we saw that rank of AB is less than or equal to rank of A and rank of B, right? Right? So, so suppose for example, let us say you are having the rank of A is, let us say, rank of A is suppose 2 and the rank of B is suppose 3. So what is the smaller upper bound of rank of AB?
2.
2. So what we do? We took the minimum of rank of A and rank of B. So in general, here both of this combined together gives this formula that rank of AB is less than or equal to minimum of rank of A comma rank of B. So this minimum comes into formula when you take both rank of A and rank of B. Okay, so rank of AB is less than or equal to minimum of rank of A comma rank of B. Is this clear? Why the minimum comes? Yes?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay, good. So the next thing is about the null space. Okay, so for the null space, so this is quite straightforward. So if bx is equal to 0, then abx is going to be equal to 0. So this means what? So if bx is equal to 0, this means what? Your x is in. So this means what?
Ma'am,
Yes,
can we write the above that column space matrix as row space? Can you write the formula that uh, as you take B11 into A11 column wise, if
hmm.
we take it at write it into row wise, how
Hmm.
can we write that?
Then it will become like this.
I want to write that problem. If
You want to write it here
yeah,
for this
yeah,
one?
yeah.
Okay, it's not a big deal. So here you see that this is the first row, right? So
Yeah.
now your first row, so let's say B11, B21, B31, or sorry, first row I have to take, right? B1. So B11, B12. This is your first row of B. So that is A11, B11 plus A12, B21, B22 plus A13, B31, B32. Is this you want?
Yes,
This is
yes,
what you want.
yes, ma'am.
Okay, good, good.
Yes.
Okay, fine.
Okay, ma'am. Yes, ma'am. Okay.
All right. So Bx is equal to 0 means that x is in the null space of B. Similarly, ABx is equal to 0 means what? X belongs to null of AB, right? So this means what? Null of B is a subset of null of AB. So dimension of null space of B is less than or equal to dimension of null space of AB. So what do we call the dimension of null space of B? The dimension of null space of B, how do we call it? Just like dimension of column space of AB is the rank of AB. Same way, what is the dimension of null space of B? Come on, rank and
Nullity. That
yes. So nullity of B is less equal to nullity of AB. Okay, so these are some relations we have for the product and the underlying matrices. Okay, I hope these properties are clear for everyone. Okay, fine. So next we are going to look at inverses. So before even moving to inverses, so in general for matrices, when do we talk about inverses? Can we talk inverses for square matrices or rectangular matrices?
For square matrices.
Yes, only for square matrices, right? So same way, so in transformations also, we can define inverses only when the domain and codomain are same. Okay, so such kind of transformations we already know they are called linear operators, right? A linear transformation from the same vector space to itself is called a linear operator. Okay, and we can define this invertible operators only for invertibility only for linear operators, not for any transformation. Okay, so an operator t from fn to fn is said to be invertible if there exists an inverse operator s such that s composition t is same as t composition s is same as identity. Okay, so the same Condition, similar condition we know in the case of matrices, right? In the case of matrices, how do we define the inverse? So A times of A inverse equal to A inverse times of A is equal to identity, right? This is how we define for matrices, right? So remember that inverse, whenever it is existing, it is going to be in it. So it means what? Given one operator, there is going to be only one operator S which satisfies this condition. There cannot be more than one operator which satisfies this condition. Okay, fine. Now, what are some equivalent conditions? Same way here, I don't know whether I have mentioned it later. So this is something. So let us see, what is the matrix representation of M of S? What is the matrix representation of M of S? Can anyone say?
N into N.
Sorry, what? See, what is your S? Your S is nothing but T inverse.
Oh, inverse operator. Yes, yes.
So, what is M of T inverse is the question. What is M of T inverse? Your S is simply T inverse. And what is M? The matrix representation of the inverse operator in terms of M of T.
Ma'am, sorry, come again.
Yes, see, you are having a operator T, and T inverse is the inverse operator. So M of T, so for T, the matrix representation is M of T. I'm asking for T inverse, the matrix representation is M of T inverse. Can you compute this M of T inverse using M of T? The answer is here.
It's I.
See, what do you want? You want this property first of all, right? So S composition T, and first of all, you also know this M of S composition T is same as M of S into M of T, right? So now can you tell me, or let me
Ma'am,
replace?
I by M. I by
Hold
MS.
on, hold on. So this is M of T times of M of T inverse is equal to I. So now tell me what is M of T inverse.
Yes, ma'am. I by M of
I
T.
by MT.
No, I is a matrix. How can you divide a matrix by another matrix?
Ma'am, wait.
If I say the answer, you will say, oh,
Ma'am, 1 minute. It's M of T.
how can it be M of T? See, I guess you people are thinking too much. It's quite simple actually. So, see, this M of T inverse is some matrix you are having. Let's say this is your A. Okay, this is some matrix B. Okay, which satisfies the condition. So, what is your B in terms of A? Which matrix has this property? B is,
A inverse of B.
yes, A. B is the inverse of A, right? Now, can you tell me the answer? So instead of B, I have written M of T inverse. Instead of A, I have M of T. Now can you tell the answer? Instead of A, I have M of T. That's all right. M
Okay,
of
M
T
of T
inverse.
of inverse.
Yes, the inverse
T
of this
inverse.
matrix I by M of T is like literally you're considering them as numbers, but when you think them as matrices, so it is simply the inverse of the matrix. That's all, right? Okay.
Ma'am, I am thinking, but
Yeah,
I
I
am
understand. Like
confused.
you all know this
Yeah.
answer. When I say, you will say, "Oh, only this much." Yeah. Okay. So M of T inverse is simply M of T the whole inverse. Okay. Good. All right. So so kind of summarizing the properties for an invertible matrix. So let's say you have an operator Fn to Fn. Okay, and the matrix representation you have an n by n matrix. Okay, so a matrix is invertible if and only if the null of T is equal to 0. Uh, yes. So the matrix is invertible if and only if null of T is equal to 0. Or in other words, null of T equal to 0 means what? The nullity is 0 or the rank is equal to n, right? Or the columns are linearly independent, or columns or in fact rows also you can say. Both are linearly independent. Okay, also mx equal to 0 has a unique solution x is equal to 0. Okay, so all of these are equivalent conditions to say that M is invertible. And in terms of determinant, we have not yet seen what is a determinant, but you already know the condition in terms of determinant for an invertible matrix. We
Yes,
have,
not equal to 0.
yes, we have seen the case in the case of 2 by 2 matrices, right? Determinant of M should be not equal to 0, right? This is the other condition. So the formula for the 2 by 2 case we already know. So if you have a 2 by 2 matrix A, B, C, D, the inverse is given by 1 by AD minus BC. You do the place change for these two entries and do the sign change for the other two entries. This is how we usually remember this formula, right? So 1 by AD minus BC, D minus C minus BE. And you should note that this is nothing but the determinant of A, AD minus BC, right? Okay, but in the case of 3 by 3, there are several ways to find the inverse. So one such way is given here. Okay, how are we going to find? So we are going to use the row elimination concept only, but we are not going to just do the row elimination only for A, but together with A we are going to augment an identity matrix. Augment means just keep another matrix together with this, right? So we are going to augment this identity matrix together and do the row operation for all these entries here. So for example, so let's say start with this matrix. Now first row operation, what I want to do, I want to bring this one here. Okay, so I want to bring the one here, so I'm flipping row 1 with row 2. So you see 1 0 1 0 1 0, this complete entire row gets shifted to the first place and the first row moves to the second place, right? And then what is the next step we want to do? We want to make this entry. So first we move to this and then we want to make this entry as 0. So R3 minus 2 times of R2, that makes this entry as 0, right? And then what I want to make this entry as 0. This and this, both of this I want to make them as 0. So first I'm making this entry as 0 by making R1 moving to R1 minus R3. Whatever operations I'm doing, remember I have to do it for the entire row, not just for the entries of the matrix alone, but for the identity matrix augmented with it. Okay, because this part is what is going to render us the inverse of the matrix. Okay, so you see that we are doing this operation for the entire row. Okay, and then we are going to make this also 0, so R2 goes to R2 minus 2 times of R3. So you see that this entry also has become 0. So we are doing this process till we get the identity on this side. So now you see that this is your identity. We started with identity on the right hand side and now we see that the identity is here and this part is your A inverse. So the process of finding A inverse, is that clear for everyone? How did we compute A inverse using row elimination? Is that clear to you? Yeah,
Yes, ma'am. Yes, ma'am.
good.
Ma'am, we can't find without the row elimination.
So,
As I
ma'am,
told you,
we
there are several techniques to find inverse of a matrix. This is one of the techniques. Okay, so you can use the adjoint formula with the determinant. So that is this kind of a formula. But in this course here we are introducing to you this, we are telling you this method to you. Okay, so already this method,
ma'am, we have to convert main matrix into identity matrix too.
yes, yes, you have to proceed till you convert this original matrix to identity matrix.
Okay, ma'am.
Okay, fine.
So using the
We will be
formula or having the elimination, do we get the different answer of the A inverse?
See, that is the thing, right? Inverse is unique. Inverse cannot be different. Whatever technique you are using, the inverse is still the same. Okay,
Yes,
fine.
ma'am.
Yeah.
Yes, ma'am.
Any other questions? Okay. So here are some more examples. So what are permutation matrices? Matrices where every row and every column contains exactly one entry as 1 and the remaining entries all are 0. Let me repeat if you don't understand. Take any row here. How many non-zero entries are there in any row?
1.
1, and that non-zero entry is also equal to 1. Similarly, you take any column, the only non-zero entry is 1 and it appears exactly once. Such matrices are called permutation matrices. Okay, so here you see that this is a permutation matrix. So also you can see that permutation matrix are like your identity matrix, the columns or rows are kind of shuffled, they are permutation matrices. Permutation of the rows of identity matrix, rows or columns of identity matrix. Okay, fine. So suppose you are having a permutation matrix, what is the inverse? First of all, will the inverse exist for a permutation matrix?
Yes, ma'am.
Because the rows are nothing but the canonical basis, rows or columns are nothing but the canonical basis, and hence they are linearly independent, and hence it should be invertible, right? Okay, so now we augment the identity matrix. Then what we are doing, we are first of all moving this one here. So we are shuffling r1 with r3, right? That is the first step. And then what we want to make this entry 0, so I can simply move this entry here by shifting the rows again. So what is the resulting matrix for me? So here once again, if I shift this row here, one more step is needed. Okay, so first I have flipped these two rows, and the next flipping 1 0 0 0 0 1, and then I am putting the last row here and the second row here. So you see I have got the identity here and the inverse here, and the inverse is also a permutation matrix. So the inverse of any permutation matrix is again a permutation matrix. That is another observation here. Is this example clear? Yes.
Yes, ma'am.
Okay,
Clear.
another
What
example.
does it mean here, the permutation matrix, ma'am? Is it only the inverse?
That's what I told you. What is mean by a permutation matrix? A matrix which contains like exactly one in exactly only one non-zero entry, that is also one in each row and column. Or you can also say that what is a permutation matrix? What is permutation? Do you know already?
Yes, ma'am.
Okay, so just the shuffling of the entries, right? So permutation matrix is obtained by permuting rows or columns of I. So what is a permutation matrix? Is that clear? Yes.
So we always having the identity matrix for finding the permutation matrix. Is that
Sorry, what?
we always having the identity matrix for finding the permutation matrix?
Yeah, permutation matrix is obtained, is defined in this way. See how are diagonal matrix defined? All the diagonal entries, except diagonal entries, all other entries are zero. That is how it is defined. Same way permutation matrix are defined in this way. Okay, by permuting rows and columns of I, whatever the resulting matrix you are getting, they are permutation matrices. Is that clear? Yeah.
Could you please take one example?
See, these are the examples. See, here, what are the rows of the identity, rows or columns of the identity matrix? So you have E1, E2, E3. These are the rows of identity matrix. So now here in this case, for example, here you see, so let's say this is permutation matrix one. So E1 you are keeping as it is, and you are shifting, shuffling E2 and E3. So I am just permuting these two alone. Or you can also E3, E2, E1. So like this you can do several permutations, right? So E2, E3, E1. All this kind of matrices, like shuffling these rows, whatever you are getting, they are like I can put E1 here, E3 here. E, this is what I have already having. So maybe I can put, what are the other options? Any other options? E2 here and E1, E3 here and E1. That's what I've written. Have I left any other options? Is everything done? All permutations? 1, 2, 3. 1, 2, 3.
Middle in E1,
And
or
none.
anything can be in E2 or E.
Yes. So E1, E2, E3, and P5. So E3, E1, E2. Anything else left? That's all right. So for 3 by 3 matrix, these are all the permutation matrix, right? And your inverse, you see for inverse you have, this is your E3, this is your E1, and this is your E2. So do you understand what are permutation matrices?
Yes, ma'am.
Okay. So if you take any of this permutation matrix and find inverse, then it is going to be another permutation matrix. It cannot be anything different from that. Clear?
Yes, ma'am. Thank you, ma'am.
Okay. So here, the next example, you can identify that you are having a upper triangular matrix. Now, for an upper triangular matrix, we are trying to find the inverse. Okay. So what is the first step? First step, what we have to do, we want to make this entry as 0, because already these entries are 0. So the next step, I want to make this entry as 0. So R1 minus 2 times of R2. So this entry has become 0. And then next, what I want to make this entry as 0, right? And then this entry, both of this I want to make it as 0. So R1 goes to R1 plus 2 R3. Similarly, R2 goes to R2 minus R3. So when I do these two steps, what will I get here? So let me write it for you. So R1 I want to replace with R1 plus 2 R3. So 1, 0, 0. And here what will I get? So 2 times of R3 means this is 0. So this will remain the same. This will remain the same. And this will become 2. And now for the second row, I want to replace with R2 minus R3. So this is same. This is same. This is 0. And this is 0, 0, minus 1. And 0, 0, 1, 0, 0, 1. So I have got identity here and the inverse on the other side. What is that you notice? Here also I have a upper triangular form. All these entries are 0. Same way here also it is an upper triangular form. All these entries are 0. So the inverse of an upper triangular matrix is upper triangular. Is that clear?
Yes,
Yeah?
ma'am. Clear, clear, ma'am.
Okay. Same way you can also see that the inverse of a lower triangular matrix is also lower triangular. Okay, so you can easily look at the steps and understand that the lower inverse of a lower triangular matrix is lower triangular. Okay, what about the inverse of a diagonal matrix? Can anyone tell? Okay, let's see. A is equal to, I am going to take d1, d2, d3. All my di's are non-zero, let's assume. Okay, so I'm augmenting with 1 0 0 0 1 0 0 0 1. For row elimination, what should be the first step? Can anyone tell? What should be the first step in row elimination? Usually, what is the first thing we see? You want this entry to be 1. Here it is already 1. Here also it's already 1. So here, how will you make the first entry as 1 here?
Dividing by with d1.
Yes. So R1 replaced with R1 by D1. So I will get 1 0 0 1 by D1 0 0. Then what's the next step?
And r2 equal to r2 divided by d2. Similarly,
Similarly,
r3.
R3 divided by D3. These are the things we want. 0 1 0 0 0 1 0 1 by D2 0 0 0 1 by D3. So for any diagonal matrix, what is the inverse? Can you tell now?
It also be diagonal, ma'am.
It is also a diagonal matrix, and the diagonal entries are simply the inverse of the diagonal entries here for non-zero entries. And if it is 0, it is going to remain 0.
Yes, ma'am.
Okay, fine. All right. Okay. So inverse and transpose of product. So let's say you have two invertible matrices A and B. Then AB and BA are also invertible. How is that so? So AB whole inverse is equal to B inverse A inverse. First of all, how is it? Okay, in terms of linear transformation, can you think how is that correct? Okay, I'm giving you a hint. Use fundamental theorem of linear algebra. What is the fundamental theorem of linear algebra? Okay, I'm giving you a second hint here. First hint already is given. So second hint, you have to use rank nullity theorem. Okay, so there is another way you can use if you know determinant properties. How many of you can immediately think about determinant property here? Yeah.
Determinant not equal to 0,
Yes.
invertible.
Determinant of A and B are invertible. This means the determinant of A is non-zero and determinant of B is non-zero. So
Yes,
this
ma'am.
means that determinant of AB
AP also non-zero.
non-zero, right? So this is the way using determinants. For using linear transformation, I give you time to think using rank or nullity theorem. How many of you can come up with a solution to this? Shall I give you time till tomorrow? Tomorrow I'm going to take the session again. Can you all try to give an answer based on this tomorrow? Okay. How many of you are taking up this homework? Let me see your hands. Okay, let's see how many of you are able to complete it. Okay, try it. Good, good. Okay, so tomorrow try and let me know whether you are able to come up with an answer. Okay, fine. So, yeah. So A B whole inverse, if assuming that with this statement is true, then AB whole inverse is B inverse into A inverse. Okay, so how can you see that? Simply you multiply AB with this, and then you can see that you can, this is associative, matrix multiplication is associative, you can switch the brackets. So this part is now identity, and then only A into A inverse, and that is again identity. Okay, so AB whole inverse is B inverse A inverse. Remember, the positions are switched when taking the inverse. Similarly, the same happens for A transpose as well. AB whole transpose is equal to B transpose A transpose. Okay, so remember, row 1 of AB transpose is column 1 of AB, right? Because rows and columns are interchanged when doing the transpose. And column 1 of AB is a linear combination of the columns of B, right? And then you can see that again they are linear combination of the rows of B transpose. So like this is very given like in a very wide angle, but if you can try it with this kind of an example, you can very easily see. Okay, for square matrices you should consider. So if you take square matrices and do something like this, you can very easily see that AB whole transpose is equal to B transpose A transpose. Okay, and when we are combining transpose and inverse, A transpose whole inverse is A inverse whole transpose. How is that so? If I'm multiplying A transpose with A inverse whole transpose and apply this formula here. Okay, so what is that formula? So let's say this is my X, so you have A, let's call this X, and this is Y. So you have X transpose, Y transpose, and according to this formula, it is YX whole transpose. Now, what is your Y? Y is A inverse. And what is your X? X is A, so the whole transpose. So how is this equal to this? Is that clear? I have just applied this formula here.
Yes, ma'am.
Okay. So what are the formulas mainly we need to remember here? AB whole inverse is equal to B inverse A inverse. AB whole transpose equal to B transpose A transpose, and A transpose whole inverse is equal to A inverse whole transpose. So these are the three important formulas we need to remember from here. So in week 6, the main topics are in matrix algebra, addition and multiplication, and then row and column space of the matrix product and matrix inverse, and then we also have matrix powers and determinants. In today's session, we have covered matrix algebra, row and column space of matrix product, and matrix inverse. Tomorrow we will cover matrix powers and determinants. Okay. So in today's session, whatever we have covered, is that clear for everyone?
Yes, ma'am.
Okay, good. So then we will continue again with week 6 tomorrow. Okay. So see you all again tomorrow. Thank you.
Ma'am, could you please
Thank
tell
you,
me
ma'am.
that what tasks you have given for
Only
tomorrow?
one task I have given, that is to check this condition using linear transformation that AB, if A and B are invertible, then AB and BA are also invertible.
Okay.
We have to prove with the rank nullity theorem, no, ma'am?
You can use rank nullity theorem. See, first of all, imagine A and B as linear transformations and then see whether you want to use rank nullity theorem, or you can come up with some other argument also. It's fine.
Okay,
Okay.
okay, ma'am.
Yeah.
Okay, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.